every type of neutron star phenomenon. Space is complicated. We make it simple. A neutron star isn't just a dead star. It's a teaspoon of it, weighing more than a mountain, a city-sized object spinning faster than a kitchen blender, and in some configurations, a magnet powerful enough to erase a credit card from 100,000 kilometers away. Every neutron star starts the same way, a massive star's core collapsing until protons and electrons are crushed together into neutrons. But what happens after that collapse branches into wildly different objects. We're going in order of how each one reveals itself, then we'll sort them a second way by how violently they'd kill you. Because on this list, close enough to observe and close enough to survive are never the same distance. The basic neutron star. We begin with the baseline because even the plainest version of this object is already absurd. When a massive star's core collapses, gravity crushes it so violently that electrons and protons are forced together into neutrons, and the collapse only stops when a quantum effect called neutron degeneracy pressure finally pushes back hard enough to halt it. What's left is typically about 20 kilometers across, roughly the size of a city, but packed with more mass than the sun. Here's the number that should genuinely bother you. A single sugar cube sized piece of neutron star material would weigh about 1 billion tons on Earth, roughly the mass of a mountain range compressed into something you could hold in one hand if your hand could survive the attempt, which it couldn't. Gravity at the surface is about 2 billion times stronger than Earth's. If you dropped an object from just 1 meter above a neutron star, it would strike the surface at a meaningful fraction of the speed of light. And because angular momentum has to be conserved during the collapse, the same way a figure skater spins faster by pulling in their arms, a neutron star inherits the rotation of a star many times its size, compressed down, meaning most neutron stars spin extremely fast the moment they're born, some completing a full rotation in a fraction of a second, right out of the gate. Here's the fact that should genuinely bother you before we even get to the exotic categories. A newborn neutron star doesn't stay at its birth temperature for long, and yet it never fully cools down either. At the moment of formation, the interior can reach temperatures of around 100 billion degrees Celsius, but within seconds, the star sheds the overwhelming majority of that heat through an enormous burst of nearly undetectable particles called neutrinos, streaming outward almost unimpeded because neutrinos barely interact with ordinary matter at all. What's left, even after that initial cooling, is a surface still glowing at roughly 1 million degrees for thousands of years afterward, meaning a cold, dead stellar remnant is, by any everyday definition, still hotter than the surface of the star that made it for millennia after the star it came from stopped shining entirely. Pulsars. Here's the twist. We didn't discover this object by looking for it. We discovered it because it accidentally started talking to us. A pulsar is a neutron star with a powerful magnetic field tilted at an angle to its spin axis that funnels beams of radio energy out from its magnetic poles like a lighthouse. If one of those beams happens to sweep across Earth as the star rotates, we detect a precise rhythmic pulse of radio energy. Some pulsars beat with a regularity so exact that, for a brief period after their discovery in 967, astronomers seriously entertained the idea that they'd picked up a signal from an alien civilization, jokingly labeling the first one LGM-1 for little green men. Here's the fact that should genuinely bother you. Some pulsars are more precise timekeepers than most atomic clocks built by humans. Millisecond pulsars, a subtype spinning hundreds of times per second, keep time so consistently that astronomers have used networks of them, called pulsar timing arrays, to search for ripples in spacetime itself. Gravitational waves too large and too slow for detectors like LIGO to catch, stretched across years instead of seconds. A dead star spinning itself down over millions of years has become one of humanity's most precise scientific instruments, purely as an accident of geometry. Magnetars. Here's the reframe. Take a normal neutron star's already absurd magnetic field and multiply it by up to 1,000. A magnetar's magnetic field can reach a quadrillion times the strength of Earth's, strong enough that at a distance of 100,000 kilometers, roughly a quarter of the way to the moon, It could wipe the data off every credit card and hard drive on the planet. The field is so intense that it distorts the physics of the atoms on the star's own surface, stretching electron orbitals into thin cigar shapes instead of spheres. Here's the fact that should genuinely unsettle you. Magnetars aren't gently powerful. Their crust occasionally cracks under the strain of their own magnetic field in an event called a starquake, releasing a burst of gamma radiation so intense that one detected in 2004 from a magnetar 20,000 light years away briefly disrupted Earth's upper atmosphere and was picked up by satellites designed to detect nuclear detonations. That single event from a star on the far side of the galaxy released more energy in a fraction of a second than the sun produces in 100,000 years. If that same magnetar were located just 10 light years from Earth, astronomically next door, the resulting burst could plausibly damage the ozone layer enough to threaten complex life. We happen to live comfortably far from every known magnetar. That distance is doing a lot of quiet, unglamorous work. Binary neutron star mergers. Here's the pivot. This is where two of these objects stop being individually terrifying and become collectively catastrophic. When two neutron stars are locked in a mutual orbit, they slowly spiral toward each other over millions of years, losing orbital energy as gravitational waves, until in the final seconds before collision, they're circling each other hundreds of times per second. The merger itself, when it finally happens, is one of the most energetic events observable in the universe. And in 2017, astronomers detected one directly for the first time, an event called G170,817, catching both the gravitational wave ripple and, for the first time ever, the corresponding burst of light across nearly every wavelength simultaneously. Here's the fact that changes everything about where the heaviest elements in the universe come from. The extreme conditions in a neutron star merger are now believed to be the primary source of the universe's gold, platinum, and other elements heavier than iron, forged in a rapid nuclear process that requires exactly this kind of violent neutron-rich collision. Estimates from that single 2017 event suggest it produced gold and platinum totaling many times the mass of the Earth, flung outward into space in a matter of seconds. Some of the gold in a wedding ring, quite literally, may have been forged in the collision of two collapsed stars, sometime before the solar system even existed. Quark stars. Here's the twist that breaks the whole category open. Some physicists suspect neutron stars aren't actually the densest, stable, stellar remnant possible. They may just be a stepping stone toward something even stranger. The theory holds that under sufficiently extreme pressure, even neutrons themselves could break down further, crushing into their fundamental building blocks, quarks, forming an object called a quark star, sometimes described as a giant self-gravitating atomic nucleus with no ordinary atomic structure left at all. No confirmed quark star has ever been directly observed. The evidence remains circumstantial, based on a handful of neutron stars that appear, from indirect measurements, to be smaller and denser than standard models predict they should be able to survive as. Here's the fact that should genuinely bother you. If quark stars exist, some theories suggest they could convert ordinary neutron star material that touches them, triggering a runaway transformation that spreads through the entire star in seconds. Meaning a quark star wouldn't just be a stranger object sitting quietly in space. It could be actively, silently contagious to any ordinary neutron star unlucky enough to interact with it. Glitching pulsars. Here's the fact that should genuinely confuse you because it breaks the one thing pulsars are famous for: precision. Pulsars are supposed to be the most reliable clocks in the universe, spinning down predictably, gradually, as they lose rotational energy over millions of years. But every so often, without warning, a pulsar spin rate suddenly abruptly speeds up, a phenomenon called a glitch, before slowly relaxing back toward its expected rate over the following weeks or months. Here's the leading explanation, and it's stranger than you'd expect. Neutron stars are believed to have a rigid outer crust and a separate superfluid interior that can rotate at a slightly different speed, frictionlessly, almost like a bowl of liquid spinning independently inside a spinning solid shell. A glitch may be the moment that interior superfluid suddenly catches up with and transfers momentum to the slower outer crust in an event similar to a starquake, abruptly speeding up the whole object in a matter of seconds. Here's the part that lingers. The Vela pulsar, one of the most closely monitored, has glitched more than 20 times since its discovery, and each event gives physicists one of the only indirect windows we have into a state of matter that exists nowhere else in the known universe. A frictionless superfluid, inside a crushed stellar corpse, occasionally shrugging inside its own shell. Black Widow and Redback pulsars. Here's the fact that closes this category on its most unsettling note: some pulsars aren't loners. They're locked in binary systems with an ordinary companion star, and instead of coexisting peacefully, they are, over cosmic time, actively killing their partner. A Black Widow pulsar blasts its nearby companion with intense radiation and high energy particle winds, slowly stripping away the companion star's outer material, evaporating it layer by layer over millions of years. The pulsar's own name borrowed directly from the spider that consumes its mate. Redback pulsars follow a similar pattern with a slightly larger, less doomed companion. Here's the part that lingers. Some of these systems have been observed with companion stars already reduced to a small fraction of their original mass, still orbiting, still being stripped, sometimes eclipsing the pulsar's own radio signal as stripped material passes between it and Earth on each orbit. We are, in these systems, watching a slow motion murder play out on a timescale of millions of years, a dead star feeding on the living one it happens to be gravitationally chained to. Neutron star black hole collisions. Here's the fact that closes this list on its most recently confirmed note. For decades, this exact type of collision existed only in theory. Astronomers had detected black holes merging with black holes and neutron stars merging with neutron stars, but never definitively caught the mixed case in the act. That changed in January 2020 when gravitational wave detectors picked up signals from not one but two separate events, each showing a neutron star being consumed by a black hole several times more massive than itself. Here's the fact that should genuinely bother you. In both confirmed events, the neutron star appears to have been swallowed essentially whole, with little to no material flung outward in the kind of bright electromagnetic afterglow seen in neutron star mergers. Meaning, unlike the 2017 event that lit up telescopes across the planet, these collisions were detected purely through the ripple they sent through spacetime itself, with no corresponding flash of light ever found, despite extensive searching. Here's the part that lingers. Physicists still aren't entirely sure why some of these mixed mergers appear to produce visible light and others seem to vanish into complete electromagnetic silence. It may depend on the exact mass ratio between the two objects, whether the black hole is large enough to swallow the neutron star cleanly before it has time to be torn apart and produce a visible flare at all. Let's sort these 8 again, a different way, not by how they were discovered, but by how violently they'd end you. On the survivable at a distance end, a standard pulsar whose radio beam, even if pointed directly at Earth, poses no meaningful danger from any reasonable distance. On the harmless but baffling end, glitching pulsars, an internal quirk of physics that poses no danger at all, just an ongoing mystery about a state of matter we can't reproduce anywhere else. On the theoretically contagious end, Quark Stars, an entirely unconfirmed threat, but one whose proposed mechanism is stranger than almost anything else on this list. On the slow motion end, Black Widow and Redback pulsars, killing their companions not in an instant, but across millions of patient years. On the sudden and catastrophic end, Magnetar starquakes capable of disrupting a planet's atmosphere from 10 light years away in a fraction of a second. And on the cosmically generous end, binary neutron star mergers violent enough to briefly outshine entire galaxies, and yet responsible for scattering the raw material of jewelry, electronics, and coinage across the universe. Every entry on this list starts from the exact same starting material, a star's crushed, neutron-packed core, and yet ends up doing something almost nothing else in the universe can replicate. It's also worth understanding just how these objects are actually found in the first place, because the discovery methods are almost as strange as the objects themselves. Astronomers can't simply point an optical telescope at a neutron star and see it the way you'd see a planet. Most emit little to no visible light at all. Instead, discovery depends on catching one of these specific behaviors: the rhythmic radio pulse of a pulsar, the X ray flare of a Magnetar starquake, or the gravitational wave signature of a merger event, each requiring a completely different class of instrument built decades apart to detect. The first neutron star wasn't confirmed until 1967, and the first gravitational wave detection of any kind didn't happen until 2015, meaning entire categories on this list were completely invisible to human science for most of the 20th century, not because the objects were rare, but because we simply hadn't built the right kind of eyes yet. Here's the last thing worth sitting with. Every neutron star on this list is technically already dead, the star that made it stop fusing anything a long time ago. And yet, these are some of the most active, energetic, dangerous, and useful objects in the entire universe, more precise than our clocks, more magnetic than anything we can build, and more responsible for the gold on your finger than anything happening inside of mine. Something can be a corpse and still be one of the most violently alive things in the sky. Not bad for stick figures on a rock.